Welcome. In this video, we will be taking a look at optimization, introducing what it means to have a global maximum, local maximum, or global or local minimum value. We'll also introduce the first few applications with business, with profit, revenue, and cost. So let's take a look at what it means to have a local extrema or a global extrema. So in the table here, we have some subdivisions of what it means to have a local extrema. So if f of x has a local maximum, we would say a local maximum occurs at a point x equals a if f of a, the functional value, is greater than or equal to f of x for all x near x equals a. So in the neighborhood, in other words, around this input, it becomes a maximum, where it's kind of a peak point on the graph. We could say a similar phrase for the local minimum. F of x has a local minimum at x equals a if f of a is less than or equal to f of x for all x near x equals a. So we have an example of both of those local extremas. So both of those would be called together a collection of local extremas. So we have local minimums on our graph here, and we have also a local max. It's not the overall, or what we'll call the global maximum or minimums, but it is kind of these peak and valley points that, notice that each of these also have a tangent slope of 0. So each one will actually carry that tangent slope of 0, these peaks and valleys, local minimums or local maximums. So when we consider the global maximums or global minimums, which we call collectively as a global extrema, the global extrema will have a functional value that is larger than the function at all values of x in the domain of f of x. So this is for all x in the domain. So we have two examples there in our function. We could say that we could categorize these as both local and global maximums. So in other words, a local maximum can be a global maximum, but a global all local maximums aren't global. So another way we could say a global maximum or global minimum is a global extrema. We also could call those overall or the absolute maximum or absolute minimum. So we have those distinctions as well. We'll try to keep to the global maximum in this course, or the global minimum for those minimum values. A couple things on those values again is the idea of critical point. So the concept of a critical point, we kind of reiterated, I believe, last class or last video, and we said that a critical point for a function f of x is where x equals a is a value x equals a, at least in the domain of f of x, where either the derivative f prime of a is equal to 0, so that would be the 0 tangent line, or f prime of a is undefined. So at either of those types of points, we would say that critical points could exist for our function. Also note here is that local maximums and minimums will only occur at critical points. So to be able to find our local max and mins of a graph, we first want to consider, again, critical points. That will be our kind of a key phrase there. So we're going to introduce the first derivative test here to test whether or not we have a local max or local min for our graph. And let's talk about that test for a moment before we jump into our first example. So the first derivative test considers critical points of a function and tests those critical points based on the first derivative. So for each critical point, we'll call C. So each of these values C are critical points. Examine the sign of f prime of x, the derivative, to the left and to the right of C. And again, C here is an input value. We could list this as a value x equals C. It's a constant where we have a critical point. That's the input. When we do the comparison, if f prime of x changes from a positive to a negative at x equals C, then f has a local maximum at C, comma f of C. So that would be the first example here. We could say that's kind of the first picture that's listed here. We will have a maximum where the graph changes from a positive derivative to a negative derivative. Case 2 is if f prime of x changes from a negative to a positive, or a negative derivative to a positive derivative. That would produce the picture that we have in the middle here, from a decreasing graph to an increasing graph around that critical point. So that would create a minimum value. Third option we could have is, what if f prime of x does not change sign? If f of x does not change sign, then we're going to have what we'll call a kind of a saddle point, one way or the other, either where it's all increasing or all decreasing, and we have that singular critical point that still again has the tangent slope of 0, but we actually don't change the increasing or decreasing nature of the function. We again call that a saddle point. So sometimes critical points can produce points that are not minimums or maximums. So we'll have to be careful about those situations. So let's go ahead and dive into the first example with a function f of x, and then we will apply our knowledge to the first application. So we want to find the local maximums or minimums, minimum values, for the function f of x. So whenever we're asked to find local maxes and mins, we first want to consider finding the critical points. So to find critical points, we want to go for our derivative. So let's go ahead and just take our derivative. We'll call that f prime of x in this case. We'll start with our f of x function, take its power rule derivative. Each of these terms we can take individually. We'll get the following: 3x squared minus 12x plus 9, and then the 2 becomes just a 0. So that is our f prime of x. We want to take that f prime of x and set it equal to 0, because we want to find where, again, our derivative is equal to 0. Where is that tangent line slope going to be equal to 0? So we want to go ahead and set our first derivative equal to 0. With setting this equal to 0, it looks like we have a quadratic function to work with here. And the first thing we might be able to see is to factor out a factor of 3 here. We can say that 0 is equal to 3 times x squared minus 4x and plus 3. And I think we can also factor that quadratic that is left. We'll take a look at doing that with 3x minus 3 and x minus 1. That'll get us a cross term of -4 and the product of 3 that we need. So it looks like if we set this equal to 0, there's going to be two factors that come out of this. One will be x equals +3. That will be one possible critical point. And we will also have x equals 1. Okay, so now that we have our critical points, these are our possible maximum and minimum values. We can now consider the first derivative test. So I'm going to do that on the side here. Here's the first derivative test. So to start the first derivative test, I'm going to pull this out as a number line. And I'm going to place my two critical points on the number line. So I have x equals 1, and I have 1 at x equals 3. So I'd like to consider again, what is the sign of the first derivative around these points? So on the top, I'm going to show what the sign of the first derivative is, f prime of x. And below the number line, I'm going to consider some test values. So let's put a different color here. This would be in blue. These are going to be my test values. So what I'd like to do is test each of these three intervals that I've just split the function up into, everything before or less than 1, everything in between 1 and 3, and then everything greater than 3. I want to test these three intervals to see whether or not my first derivative is positive or negative. I'm not really concerned with the value of the derivative other than its sign. I really want to know if it's really going to be positive, which means increasing, or a negative derivative, which means the function is decreasing. So we don't have to be super fancy with our test values. We just want to pick values that are easy to work with. And so we could say that 0 could be a good test value in the first interval. We could just choose a +2 in the middle, and we could choose, 4 on the outside. So we don't have to be fancy with it. You don't have to use, long decimal numbers. It's okay to be simple with our test values. So each of these test values, I'm going to go ahead and evaluate in the first derivative function. That will be f prime of 0 to start. And again, I'm looking for the sign of that test value. So we have f prime of 0. If we look back at our derivative function, that's on the top here. Let's just highlight that. We're going to go ahead and evaluate 0. It looks like if we evaluate 0 here, the first term is 0. The second term will be -0 or 0, and then we'll have 9. So the first derivative at 0, that test value becomes 9, which means we have a positive first derivative that's greater than 0. So in other words, I'm going to kind of put a positive sign here and maybe even an arrow. You could use either or both of these to kind of highlight what's happening with the graph. That means I'm going to be increasing all the way up to that first critical point because my first derivative is positive. F prime will test at 2, so f prime of 2. We'll go ahead and do that. We have 3 times 2 squared minus 12 times 2, and then 9. We'll go ahead and try to simplify this structure a little bit. We have 2 squared is going to be 12 minus 24 and then plus 9. If we add these items together, I think we get a -3 when we're done. 21 minus 24. And so this is a negative value. This is less than 0. And so we would say that we're going to have a decreasing slope here. the function will be decreasing and have a slope that is negative over that middle interval. We could assume maybe that this next one's going to be positive, but let's just go ahead and check it out. F prime at 4, we'll evaluate our first derivative again, 3 times 4 squared minus 12 times 4 plus 9. So we have 4 squared is 16 times 3 would give us 54. Or 48, excuse me, 48. And then minus 48 again, and we'll have a plus 9. So these will cancel. And it looks like we get 9 again, which again is going to be greater than 0. Again, the value there doesn't matter. The only thing that matters there is our sign. So that would be positive, increasing again there. So we go from a positive derivative to a negative derivative to a positive derivative again. And even by this kind of line graph that we created here, we can kind of determine here that we have a maximum and minimum at these two places. Since we go from a increasing interval to a decreasing interval around 1, we can say that's going to be a local maximum. One thing that we'll want to do is to consider what's the actual functional value, f of 1. We plug in that value to the original function. We'll find that functional value to be 6. So this point here, we'll call 1, 6, is a local maximum value. Of f of x. And we could also say that 3, and again we'd want to find its functional value. If I said f of 3, if we look back to the original function and evaluate 3 in the original f function, we'll find 3 to have a functional value of 2. Go ahead and double check that later on if you'd like, or pause the video to do that. So the conclusion here would be the point 3, 2 is a local minimum value. So in other words, the local maximum will be found at 1, and that local max is the height of 6. And then our local minimum will be found at 3, and that local minimum is at the height of 2. There's our two values. So this first derivative test is helpful to consider now where we might find maximums in some business applications. And we're going to enter into one of those right now. This is going to be the application of the cost function. So let's consider the definition of a cost function and a couple other related functions. So a cost function we'll call C of x, capital C of x, is the total cost to produce x items. So when we think of C of x, the output is always talking about a total cost to produce x items. The marginal cost function we'll call C prime of x is the rate of change of the cost function, And another way to consider that is it's kind of the approximate cost of making that next item. We don't use that as much, but the rate of change of the cost function would be our main application there. The average cost function we'll call C bar, and there should be a little x here, so we'll put that in here. C bar of x, C bar of x, is defined as the cost function C of x divided by x. So it's quite literally just the average of the cost function at any moment in the production. So at any production level x, we could take on average how much each item will cost. And so when we consider the units here, total cost would be in dollars, right? That would be our units usually for cost. The marginal cost would be rate of change. So that would be the cost per item, how that is changing. And again, cost for average cost, then units again will be, again, dollars per item. Again, marginal cost is thinking about instant rate of change. Average cost would be average rate of change. They do have the same units, but they are looking at something, a concept that is quite different. So let's go ahead and dive into this portable music player example. So company sales data has shown that the cost to produce portable music players can be given by the function C of x equals 700 plus 20x plus 0.01 x squared dollars, where x represents the number of portable music players produced. So how much will it cost to produce 55 portable music players? Well, if we want to just consider total cost, we know we could just input 55 into our C of x function. So to start out, we could just say, what is C of 55? That's the total cost for producing those 55 players. We have our 700 plus 20 times 55. And we can input our 55 squared in that last portion. If we go ahead and evaluate our expression here, our function will have an output here of $1,830 and 25 cents. That would be the total cost for 55 players. The second question we have is how much does it cost to produce the 101st portable music player? Well, we can consider at least an approximation to this in considering the 101st item is going to be very close to the marginal cost function at 100. So if we think about the marginal cost, the secondary explanation is the approximate cost to make the next item. So if 101 is the next item, we've produced 100 items so far. And so we'd like to consider again the marginal cost, if we can, C prime at 100. That's really what we're kind of shooting for on part B. So first we'd like to get C prime of x, and then we'll evaluate at 100. So let's go ahead and for that C prime function, C prime of x, we can take our original function up at the top and take its derivative. So we have the derivative of 700 would be 0, 20x becomes 20, plus 0.01x squared is going to be 0.02 times x. And now if I evaluate this C prime at 100, C prime of 100, we'll see that this is going to be 20 plus 0.02 times 100. And we can say that's going to be 20 plus 2, which is going to be $22 per item. So that's the rate of change at which the cost is changing right then and there. And so since the total cost is changing at that rate, we can consider that's an approximate cost to produce that next item. Part C takes a look at average cost. So calculating what is the average cost for the first 82 music players that are produced. Well, this would be our C bar function. We could say that we want to calculate C bar, in this case, C bar of 82 to be specific, the average cost of the first 82 music players. We can say that's the cost of 82 music players divided by the number of music players produced. That would be 82. So we can go ahead and again evaluate our original cost function, C of 82. That's the function on the top here at 82. If you go ahead and calculate that C of 82 value, you can calculate that here to be 2,407 and 24 cents. And dividing by the number of items, 82, we can get an approximate solution rounded to the nearest cent. Looks like about $29.36, again, per item. So that would be the average cost per item for the first 82 items. So we have marginal cost, average cost, and then just the base cost or total cost. Let's continue with our work here, and we'll take a look at an application building off of cost, which is the revenue and the profit functions. So starting with the revenue function, we'll call this the function R of X. This is the total revenue or income received from selling X items. So that would be an income revenue function. The marginal revenue function we call R prime of X is the rate of change of that revenue function, or we could say the approximate revenue received from receiving the next item, or producing, or in this case, selling the next item. The profit function we'll call P of X. This has an equation related to revenue and cost. This is the revenue that we take in minus the costs that go out. So revenue minus cost will be my take-home profit for selling X items. And again, this is total profit. And the marginal profit function is P prime of X, rate of change of the profit function, or the approximate profit earned for selling the next item. Okay. So the next question that we're going to consider is looking at this idea of profit. So let's go ahead and take a look at that first. Given the cost function, C of X, and the revenue function, R of X, we want to find the production level that will maximize profit. We're going to get right to it. So we want to know at what production level, that's a X input here, what production level will maximize profit? Well, how we have to go through that? Well, we considered maximizing a function by taking its derivative and setting it equal to 0. So that's not going to be any different here when we want to maximize, notice, profit. So kind of the end goal here is going to be finding this P prime of X, the derivative of the profit function, and setting it equal to 0 in finding that production level X. So that's what we should be thinking as our end goal. So let's go ahead and do the steps to get there. I first need a profit function. So we know profit, again, is, by definition, the revenue minus the costs. So we can say revenue minus costs. Our revenue here is 100x. And then we're going to subtract away the cost function. And there's certainly some simplification we could do here with distribution. We're going to distribute the minus sign for each of these terms along the way. So let's go ahead and do that. We can rewrite this a couple times just to be very clear. We have 100x, we'll have negative or minus 880 plus 70x, and then minus 0.01x squared. Now, just to kind of clean this up, I kind of like putting my leading terms or the highest coefficient term there, or exponent term first. So we have p of x function written one more time. We have the negative 0.01x squared. The 100x and the 70x become just 170 times x, and then we'll have a negative 880 as a constant. We can go ahead now, taking a look at this, I think it's a good time to go ahead and take our derivative, find p prime of x, the marginal profit function. We'll have negative 0.02 times x plus 170, and then again the constant goes to 0 when we take its derivative. So we now can set this derivative equal to 0. So we'll go ahead and set this equal to 0. And solve for that production level. There should be only one solution here. We have 0.02x if we add to the left, set equal to 170. If we take one more step to divide both sides by 0.2, we should get a result. So divide by 0.2, and this, hopefully we'll see, gets a result for us of 8,500 items. We'll give it as just the number of items. And this would be, again, the production level that will maximize profit. So any more items will decrease our profit, maybe because our costs will increase to the point where our profits are diminishing. So 8,500 items is going to be the maximum. Sometimes there's going to be a follow-up question to this, and to ask what is the maximum revenue, or in this case, the maximum profit. And again, we can answer that question by just going over to the profit function again, P, and evaluating at our production level. If you go and do that in this question, P of 8,500, our projected profit here, that is the maximum profit for this business, would be $721,620. So that would be our maximum profit in this case. Second question on this is asking, what about the average profit? So this is average profit when selling 75 units or 75 items. So if we want average profit, we could say that is similar to the cost average. We could say P bar of X again would be the profit, total profit, divided by the number of items. In this case, we're most interested in P bar of 75. So we could say this is going to be P bar of 75 items or units is the profit with $75 divided by that many units. So P of 75 divided by 75. So again, we're using this profit function, and I'll just highlight this right in the middle of our page. When we're using the P of something, we're using the profit, the total profit from 75 items. If we evaluate that function at 75, we should get a value of $11,813.75 for that total profit. Again, if I want to take the average, I just want to divide by the number of items I've sold. So that would be 75 units there. We can take that division with the total profit divided by 75, and we'll get, really this is an approximate solution. Doesn't go perfectly even. This would be $152, or 57, excuse me, and 52 cents. That would be, again, average profit per unit or per item for that. Okay. Wanted to give you guys just another reminder. We looked at the first derivative test. This is the second derivative test we looked at in our previous section 2.6. This was another way we could test critical points if they were maximums or minimums. Sometimes it'll be a question, maybe, of whether or not we should use a first derivative test or a second derivative test. And here's one way to maybe consider which one to use is if we can easily find the second derivative of a function, the second derivative test is a really helpful tool. If it's really a more complicated function where the second derivative is not easily obtained, then the first derivative test can be actually a more value since the second derivative might be more complicated. So just a little rule of thumb. So let's consider a function on a closed interval. And I think in this case, since we have a power function, let's go ahead and consider using a second derivative test the whole way through. And again, I'll try to reference our definition a little bit later on as we go through. But again, we're going to be testing these critical points into a second derivative function instead and considering its concavity. So let's go ahead and consider this function on a closed interval. So we have an f of x function. This is a cubic function on the closed interval from 0 to 5. So first, let's go ahead and consider what are our critical points specifically over that interval 0 to 5. So we're going to go ahead and do that. We have f prime of x defined first. We can do that with the power rule. We get 6x squared minus 30x plus 24, and then the 7 becomes a 0 in that derivative. We can continue that process with setting this function equal to 0, the derivative. we'll go ahead and again factor this. Looks like we can take a 6 out of this expression to make it 5x and then plus 4. And it looks like we get 2 critical points out of this. And we'll again verify that these are in the right window. This would be x minus 4, x minus 1. So we could say that we have 2 critical points. One is going to be at x equals 1. And we'll have another critical point in the interval x equals positive 4. So both of those, again, are in the interval 0 to 5. We just want to double check that that's true. And we also want to consider the endpoints here as critical points in this closed interval. That's something different that we have to consider. With a closed interval, we want to think about this value of 0, x equals 0, and x equals 5 as an additional critical points. These could be maximums and minimums of the function because we're only looking at that specific interval from 0 to 5. Those endpoints would have to be considered. So let's consider now determine where the function will have a local maximum or minimum. So let's go ahead and take, I said that we were maybe going to consider just a second derivative test, and let's do that in this case. We'll be able to kind of recall the process for a second derivative test. Since we have all these critical points lined up for us, and we'll certainly need to take their functional values at some point, we'll list those later. If I consider the second derivative test, I need a second derivative, or f double prime of x. So if I take the f double prime of x here, it's not a difficult derivative to take. We'd have this as 12x and then minus 30. And now that I have that second derivative, all I'm going to do is, again, test these 4 values, or really the 2 values in the middle, to consider whether or not we're going to be concave up or concave down when we hit, the first 2, that would be the -1 and the 4, those interior critical points. So let's consider first, we have f double prime at 1. If we evaluate here, we'll have 12 times 1 minus 30. This looks like it's going to give us -18. This is a negative value out of the second derivative. So let's consider what's happening here. Since 1 is a critical point, it's either going to be here, hopefully a maximum or minimum. And since our second derivative gave us a negative value here, we are in the category of a concave down structure, and therefore a local maximum. So whenever our second derivative at the critical point is less than 0, that's like part A here, we will give ourselves a local maximum at that point. So we would be concave down. Therefore, this point will be a local maximum. So let's go ahead and maybe just fill this in. We would say that the function f of x will have a local maximum again with a concave down structure on f double prime of 1. If I look at the functional value at 1, the actual point that we're going to be considering, f of 1 here, this is 1 comma 4. This is where the functional value will be, 1 comma 4. So f of x will have a local maximum at 1, 4. And even at this point, we hopefully know kind of from our kind of algebra skills, we kind of know what this function shape is. We have a shape of a cubic function that is increasing since we have a positive first term. We should have a function here that looks a little bit like this. And I think what we've kind of just found is that first critical point in our interval is that local maximum. We can kind of consider that as the 1, 4 point. And again, if we can, let's go ahead and kind of think simply about this. I think that second point, we should have some good intuition that x equals 4 should be a minimum value. Let's just go ahead and verify that with the second derivative test. If we do double prime, f double prime at 4, hopefully we see that this is going to be a positive value. So we have 12 times 4 minus 30. I think that's going to give us a positive 18 when we evaluate. That's greater than 0. So if our concavity at that point is greater than 0, that means we're concave up. And just like our little kind of picture here, our intuition hopefully is telling us that that is going to be a local minimum. So f of x will have a local minimum at, again, the point of here 4. And again, if we want to consider what the value at 4 is going to be, if you plug that into your original function, f, that's the original functional value, we should end up getting a functional value of 4, negative 23. And again, we're finding that using our original f function, f of 4 equals negative 23. So those are two of the critical points. If we have those, I think we can work out these endpoints just by looking at the little sketch that we've drawn here. The other 2 points were going to be x equals 5, comma something, and 0, comma something. So down on our x-axis there. And it's pretty clear here, I think, based on our shape, that we'll have another local maximum value at the value of 5. If we look at the functional value of 5 in our f function, f of 5 is just going to give us negative 12. So we'll have 5, 12 as a local maximum as well. And we'll list that on our little graph here. And then the last point at 0, f of 0, we look, will only give us a negative 7 for that functional value. Everything goes to 0 except the constant negative 7. And this value is going to be a local minimum. So 0, negative 7 would be an additional local minimum. So 0, negative 7. So f of x will have a local maximum at 1.4 and 5, negative 12, and f of x will have a local minimum at 4, negative 23 and 0, negative 7. So each of those 4 points are defined there. Another kind of benefit that we can get from using a second derivative test is we automatically have the second derivative to work with inflection points. So that's the next question we have here. What are the inflection points or point? If we take a look at our second derivative, we really want to find where the second derivative is going to be equal to 0. So if I go ahead and set this second derivative equal to 0, we could go ahead and find that value of the inflection point. So looks like we would get 30 equal to 12x, and x would be equal to 30 divided by 12. For us, looks like we can reduce that a bit here. Looks like each of those values reduced by 3. That'll give us 10 over 4, or we could say that's 2.5. 2.5 for that inflection point. If we're looking on our graph, 2.5, I didn't draw it perfectly, but that's again splitting these 2 points at the input of 1 and input of 4. So x equals 2.5 would be our inflection point. And if I wanted to consider where my intervals of concavity are, where I'm concave up and concave down, again, I could look at my kind of reference of the problem that I already have here, and I could say that my first segment here from 0 all the way to my inflection point, that's negative 2.5, this would be a, let's take a open interval here, open interval from 0 to 2.5, we would say is going to be a concave down. All that region is concave down. And we could say from the inflection point 2.5 all the way up until the input of 5 is going to be concave up. Now, even looking at this result, I'm tempted to think, oh, well, we just divide the interval that we used by 2 and just split the difference. Well, that might be a dangerous assumption when we're given other problems. So it's just a coincidence here that we get 2.5, which happens to be right in the middle of the interval. That's not always the case, generally not, but it just happens to be the result in this problem specifically. So try not to maybe make that conclusion from this result. But we do have one concave up interval and one concave down interval. We have a couple more things that we'd like to take a look at in terms of graphs, specifically some derivative graphs and second derivative graphs for a few wrap-up problems. One problem considers the first derivative, the second derivative, and the functional value for a given point. So given the following information, decide if the point is a local maximum, a local minimum, or neither. So we have a functional value 2 at 7, or functional value is at 6 for an input of 2. The first derivative is equal to 0, and the second derivative is equal to negative 3. So if I wanted to break down here what these mean, well, the functional value is just where the point is. The point is at 2, 6. That's all that tells me, is there's a defined point at 2, 6. The first derivative set equal to, or being equal to 0 tells me that we do have a critical point at 0. So this is a critical point. So that's a good start. We need to be a critical point to be a local max or local min. And the last value tells me f double prime of 2 is equal to -3. Well, that means I am concave down. So if I put all three of those ideas together, that shows me that I'm a concave down, I am a critical point, and that critical point is measured or lies at the point 2, 6 on my graph. If I just draw that out, it looks like this critical point becomes a local maximum. And that's what we'll list here for the value 2, 6. So we could say that the point 2, 6 is a local maximum of f of x. Now to finish up, we'll take a look at a derivative graph. We want to do a similar thing just by looking at a derivative graph. The values on the top of this number line indicate the value of the derivative, f of x, or f prime of x, over those intervals. And we'd like to know what's happening at these individual values, both 4 and 7. So if I look at the points 4 and 7, these values are by nature the critical points, because these are where our function's derivative is equal to 0. That's what these dots will represent. So if our derivative is equal to 0 at 4, and we have an increasing or a positive derivative here, our function is increasing, the derivative is positive. In between 4 and 7, we have a negative derivative. That means our function is decreasing. And then from 7 onward, we have a increasing function or positive derivative. At the value f of 4, it looks like at that point of the function, we actually have a local maximum. We will have a local maximum here. Because by definition, we go from a positive derivative to a negative derivative. In a similar statement, we could say that f of 7, at that point in the function, we will have a local minimum, because we go from a decreasing portion of our function to an increasing portion of our function. So we can call that a local minimum value. So with a first derivative graph, the only thing we can determine is if we are a maximum, a minimum, or nothing. We cannot determine whether or not we are an inflection point. That's not for the first derivative to decide. It doesn't have that power. The last graph that we'll take a look at is the second derivative graph. So these are second derivative values, f double prime. So this tells us we go from negative to positive, and then back to positive in between the value 6. So let's take a look at f2. f of 2, notice that we are negative in our second derivative. That would mean we are concave down over the first interval. We are concave up over that second interval from 2 to 6. And then the plus sign, again, we're going to be concave up again. But again, our second derivative is 0 at both 2 and 6. So we want to determine whether or not we have an inflection point, a maximum, a minimum, or nothing at each of these points. So if I considered f of 2, this is where we go from concave down to concave up. So in other words, if I had concave down to concave up at this point, we consider that as, again, a change in concavity. So f of 2 would represent an inflection point, a change in concavity. At 6, f of 6, we could consider we're going from concave up portion of our function to another concave up portion of our function. Here we could say, well, there's actually not anything happening, or at least no one of these three. That's not a maximum, it's not a minimum, and it's not an inflection point because we're not changing concavity. So this would be actually nothing. And we can kind of draw that by considering we're concave up for a portion, and we will level out for a moment and then continue concaving up. So this point that kind of levels our second derivative, this could be somewhat of a shelf point or saddle point, but we're not actually changing concavity, and so there's really nothing happening at the graph. At least it's not one of these three maximum, minimum, or inflection points. So the only thing that a second derivative graph can determine is if we are inflection point or if we are nothing at all. It does not determine maximum or minimum. That is not possible with a second derivative graph. So thanks for sticking with us for this lesson. Look forward to seeing you in the applied optimization. We'll learn a few more applications in the section 2.9.